About 3 weeks ago, guys, what did this glorious salt and pepper get up look like? But now, less bald. Why? What did I use over the last 3 weeks? Keeps for men. We got our hair back. I don't know, it's a weird one. All right. Cool. Realistically, don't care about keeps. I don't think I'm going to go bald. Pretty sure I'm past that point. I hope that I'm getting grayer every year. I hope that, not hope, eventually I'm just going to commit. I'm going to go straight white. So like Gandalf the white. I'm not going to let it be gray. I'm just going to go pure white. And I'll have Edelin bleach it and just have it be like paper. It's going to be awesome. Cool. Zeros of polynomial functions. This is the big kind of climatic moment where everything factoring that we've used before starts to really apply. And all of a sudden we get to go to bigger, cooler, neater polynomial functions. So, couple things. We have two little theorems to start with, followed by a big, it's not a theorem, you could call it a theorem, but it's really just an operation that we do. We'll see it. You might have seen it last year in Algebra 2. I'm not sure. To start this off, to find the zeros of a polynomial function, what do? The F word. We factor. Now, run me through the list real quick, because that list that we've kept using really and truly only applies to quadratics or things that factor nicer, but there's too many caveats to add there. First thing you always check with factoring is what? GCF. If it's a binomial, you hope it is a difference of squares. Give me an example of a difference of two squares. X squared minus 4. Do you know the square root of both of those terms? X and 2, right? How does it factor then? X minus 2, X plus 2. Awesome. Okay, what if it's a trinomial, a threenomial is how I word it. First thing you check for. So we've already done GCF, sorry. We've now moved on, we're at a trinomial. Coefficient, what do you hope the leading coefficient is? 1, because if it's a 1, you may get a chance to use what? The shortcut. If it's white, don't write. We could probably switch that up. If it's ugly gold, hold your pencil. Stupid. All right, here we go. Check it out. X squared, can you see that? How about gray? Can we see gray okay? Okay. It's like a little bit of black in it. All right, check it out. X squared plus 5x. We'll do minus 6. You do not have to write this one. You can, but you can not also. All right, GCF doesn't exist. It's 1. It's uninteresting. I see that this leading coefficient, although we never write it, what is the number here? 1. So I'm going to phrase this because I want to make sure that we can use this and we agree, because I ask people this question a lot, especially if they're getting help. How many x squareds? There's 1 x squared. Because when I ask that question, I'm really asking what is the coefficient on the x squared? How many x's? 5 of them. Why did you say 2? That's what I'm expecting. How come 2? Because you're still talking about the x squared, right? Now, notice though the language that I use, and I can clean this up. There is 1 x squared. How many x's? Now, that's not really formal. If I wanted to, if I could make it wordier, how many x's to the first power? There's 5 of them. It's this one. How many x to the zeros? Negative 6 of them. That's a trick question, sort of. What's anything to the 0 power? 1. Except what? You have a calculator. Do me a favor real quick. Do you guys know what 0 squared is? You know what 0 cubed is? Okay, what's 5 to the 0? 10 to the 0. A million to the 0. Follow-up question. What's 0 to the 0? What's it say? So, this is a weird thing, calculus idea that we're not going to get to see this year. Give me a number, any number. 0 to 0 is, say it again. Sometimes it's 5. Sometimes it's 1. Sometimes it's negative 12. It's just, it varies. It is what is known, here's a fun thing, indeterminate. It's a special thing in calculus that happens. But, all right, I'm just so excited about math. Cool, I want to factor this. I do that. What does it make? Wrong thing. Negative 6. I now need factors of negative 6 to add up to 5. Can you find them? What if I do 1 and... Ooh, careful. 5 and 1 won't work. Careful. 2 and 3 don't work, I don't think. 1 and 6. One of them should be negative. It should probably be that one. Okay. If and only if this is a 1 and you find these numbers, is there really any more work that needs done? We can just write our answer. One of my factors is x. What else? Minus 1? How about the other one? Try again. Plus 6. Cool. Okay. That's our shortcut. It is super helpful as long as you remember it. Hypothetically, let me think this out. I'm going to change this to a 2. And again, you're not writing, gosh. While I'm thinking out this middle number, find me a good way to associate gray with don't write it. If it's gray, you should wait. That's so stupid. Cool. Ooh. Yeah. Kendrick over here suggests if it's gray, put the pencil away. Yeah, I'm good with it. We're going to get one for each color. This is different. Still a trinomial, but the leading coefficient's not a 1, which means shortcut completely out. Can't use it. I'm still going to start the same. 2 times 6 gives me 12. And factors of 12 that add to 7. 3 and 4. Okay.
You changed it?
Yeah, I erased it and changed it. Yeah. Okay. 3 and 4. The mistake that I see, I want you guys to pick it out as well. I'm going to take this trinomial, I like to call it a trinomial, to make it a four-nomial so I can group it. This is the mistake that I see people doing, and I want you to tell me what they've done. This is not right, Huggins. Don't write this very last line. What has this person, me, I guess, done wrong? It's not the shortcut. That's it. Like, that's a whole mistake. Instead, we rewrite this with 4 instead, yeah? Do you want to finish this problem? Like, should I talk the rest of it out? Okay. So check it out. These magic numbers 3 and 4 are only there to replace which of these 3 terms in my trinomial? The 7. So check it out. 2x squared is still the same. But instead of 7x, I'm going to say plus 3x plus 4x. Is that still 7x? It's just written with 4 terms. Plus 6. I would have switched the order on mine, just so you know. But it still works. The reason we do this is because now we can make 2 groups that are equal in size. What is the GCF of this first group? I don't think a 2 goes into 3. It's just x, right? What would it leave behind? 2x plus 3. Now, whatever the GCF is here, hopefully, and not hopefully, whatever it is, whatever we take out, had better leave behind what? 2x plus 3. What goes into both these? It's the GCF, so that's cool. Plus 2, what stayed inside? 2x plus 3. Can you tell me the 2 factors that we found? X plus 2 and 2x plus 3. Cool. As we look at it, doable. Okay. Now, couple questions for you. In any of the situations that we just looked at all 3 of them pretty kind of close. How many factors did we find? 2. What was the degree of this function? Huh. What about on the previous one? As a degree 2, how many factors did we find? 2 again, right? I don't remember what they were, but we found 2 when we used the shortcut. On a difference of squares, you found how many factors? 2, which means seemingly you're always going to find how many factors for a quadratic. Might they repeat? Like, could I have x minus 2 times x minus 2 show up somewhere? We get the same factor, but it shows up twice, which means how many roots? 2, every single time. All right, we are going to hit like 2 big theorems right off the bat. Sorry, yeah, 2. And then we're going to jump into doing some pretty cool stuff. Awesome. Do you feel better as a factorer now than you did a month ago?
Yes.
Do you feel as good as you were last year yet? Okay. Do you feel better now than you were last year then? Cool. Check it out. This one's going to be weird because we get a couple like big bullet points right off the bat. This is a really important idea, one of the most important ideas in all of algebra. Our first topic, as we're looking at these polynomial functions, we are going to give ourselves in all caps because of how important this is. The fundamental theorem, and I will write out the real word this time. The fundamental theorem of algebra. All right. I would assume that just based on the name, the significance is already like clear. It's fundamental to the study of algebra. Okay, shorthand suggestions? It is FTA, 100%. This is like, so this isn't, to my knowledge, like really truly formal. I don't think you would find a single math teacher in the entire country that wouldn't know what you're talking about if you said, hey, we're talking about FTA in calculus or pre-calc. They would know what you're referring to. Okay, check it out. Super easy. We're going to write the really like formal version of it, and then we'll see the shortened version as well. If f of x is a polynomial function, I'm just going to say poly. I'm going to call it polyfunc, but I'll write the real word. Of degree n, and then I'm just going to specify where, what do you think n needs to be greater than to not be boring? Can you think of a first degree function, x to the 1? It's a line, like there's a bunch of them. Mx plus b is a first degree polynomial. What about a 0 degree polynomial? Is that interesting anymore? Anything x to the 0, it's just a horizontal line. Okay, as we're looking at this, we're going to require that n is greater than 0. If you give me a polynomial and n is greater than 0, then f of x has at least one root in the complex numbers, which I'm going to use this Blackboard C. Guaranteed. If you give me a polynomial function of any degree that's not 0, anything bigger than 0, you're going to find at least one root in the complex numbers. Okay, this is misleading, because if you think of something that factors like x minus 2, like let's just say it's the function x minus 2, its root occurs at x equals 2. Can we make that mental math without rewriting it? Y equals x minus 2. If you set it equal to 0, you get x equals positive 2. Okay, my root is 2. Did we just break this? If I find a function, a polynomial, who has one root and it's at x equals 2, is this broken or not? Discuss with your neighbors. I need more than just yes or no. I want the explanation as well. I'm going to do attendance while you guys are talking about that. I'm calling you in a minute. I heard it breaks it from over here. Are you sure?
I read it again and I said no.
Okay. Anybody say yes? Okay, this is a weirder question. Is x equals 2, the number 2, is it a complex number? It is. It's a sneaky one. It's a complex number of the form a plus bi, where b is equal to what, Fern? Love it. Still complex. Every number that you've ever dealt with is complex. If b is 0, it's a complex number with the imaginary part being 0. Cool. Everybody but Bea?
Yeah.
Okay. So, check it out. This is maybe not that big of a deal right now. Everything has a root, is essentially what that's saying. If it's a polynomial, it'll have a root. Here's the bigger part. So, in mathematics, you get a few different things. Thinking all the way back to algebra or geometry. Do you remember what the word corollary means? Or do you remember seeing it? Ooh, I don't know how to spell it. Corollary, 1 or 2 R's, do you think?
2 R's.
That's my guess too, but we'll see. Oh my gosh. Control A. I don't think so. That felt right. 1 R. 2 L's.
Wait, there are 2 R's.
What? Oh, okay. So, yes. Poorly worded question. I wish I knew how to make it do that. Corollary. Well, I used to do it if I double tapped or if I pushed a button on my pen. but it makes a little circle, and it used to be really nice to point at stuff, but I don't know how to make it do it. Okay, do you guys ever remember seeing the word corollary? Do you remember seeing the word theorem? Okay, we're going to take a little time travel trip. What's a postulate compared to a theorem? Which one do we have to prove? Theorems. We prove theorems. Postulates are like the base that we just assume to be true. There's no need to prove it. Okay. Corollaries are immediate implications from a theorem. So this may not seem that meaningful to you because all I've really said is, hey, you can find the roots of a function if it's a polynomial. That's all this says. The corollary is a follow-up that is going to be much more applicable to us. The corollary to the fundamental theorem of algebra tells us this. A function, and it's a poly, and I'm going to just write polyfunc. A polyfunc of degree n has exactly, and we're going to pause right there. I want you to imagine any line, so a linear function that's not just horizontal. Okay, get a picture in your head. You don't have to draw it on your page. How many times did that linear function just cross the x-axis on your graph? So check it out. Here's the x-axis. Here's a line. How many times does it cross? How about now? How about now? Once. How many times will it always cross? Okay, think of a quadratic. And this is where things get a little bit weird. Okay. If it's gray, put the pencil away. All right. So cool. All right, it's actually all this. I'm going to use a bunch of different colors. How many roots does this one have?
3.
Why 3? Why 2? So I think I know why 3. I agree there's one there and one there. You might have been looking right here. You might not have been. I'm not sure. Okay, how many roots does this quadratic have?
1.
Are you sure? Are you sure? Are you sure?
Yes.
I'm not.
Says 2.
So it's 2. Something unique happened about it though. What did that factor or what did that root do? It touched and turned, which meant that single factor or root showed up twice. We had to write it twice, right? It'd be some factor squared. Okay, last one. And these are going to get weird. What about this one? Because if you wanted to solve it, you would have to use a quadratic formula, and you're going to get a number plus or minus another number, right? Which means a number plus is a number, and a number minus is a number. There were 2. They just happen to be imaginary, right? Okay, if I were to sketch a third degree function, how many roots are you going to find? Probably 3. Would you ever find 4? That'd be weird. Here's the corollary. If I tell you that it has degree n, then it has exactly how many roots do you think? N roots. Every single time, n will always match. If it's a 5th degree function, you better find me 5 zeros. It might be 1 that's repeated itself 5 times, but that's okay. 5 roots. 5 factors. Okay. This is a more important idea. Like, this is important. This is the part of it that I care about. The little follow-up to this theorem. All right, we're going to switch colors and switch modes. You're going to miss an important idea. Make sure you look at notes when you get back, okay?
I'll just stay real quick.
Okay. Next one. Sounds ugly. We are going to write the linear factorization theorem. The linear factorization theorem. I'm going to use THM. All right. The linear factorization theorem. This one is not important enough that I'm going to call it LFT, but that's what I would call it. For the linear factorization theorem, we have the following. If f of x is an nth degree polynomial, then f of x can be written as, I'm going to let you guys catch up. If we have an nth degree polynomial, then f of x can be written as the product of n linear factors. And I'm going to even sneak in linear prime factors. And I'm sorry about that. Okay. We have started alluding to this already. When I made you guys divide to see if something was a root and then continue factoring, we wrote the f of x equals first factor and then the other one, and then we kept breaking it down. And we did that on the quiz. I think you probably did it on your new one. What this really means is that we can write any function, and this is just a kind of example of this. F of x, there might be a number out front, a. It could be 1, so maybe you wouldn't write it. But it could look like this. X minus c1 times x minus c2 times dot 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 all the way down as far as you need to go. X minus cn. When I make the stretch or the leap to generalizing like this, does it make it feel so much harder to everybody, or do you know what this is saying? You guys should start playing poker because I can't get a read on anybody. Do you understand what this is telling us? Okay, so some of us might. If C is a root, C1 is a root, and C2 is a root, C3, so forth, they're all roots. All we're doing is saying, look, we found n roots. Now there's n factors that can be written as x minus something. So like when we factor stuff and we might find the factorization is x plus 1 times x minus 2 times x minus 3, we have just written that thing as a product of 3 prime factors. That's all that this is telling us. Okay. Let's go ahead and get to the big stuff. Cool. All right. What's the most important color up here? Cool. I wish I'd left green because green's my favorite. We're going to use this theorem here, fundamental theorem, and the linear factorization theorem here to use this big idea. Okay, the real focus of today is how do we factor bigger stuff, and this is awesome. I think so. So our topic is we are going to talk about the rational and is there a symbol for rational? Why is it a Q? Quotient. The rational zero test or theorem. We'll call it a test here. All right. This definition is going to feel a little bit different. Right off the bat, we're going to have a polynomial function. And I'm going to write it in that ugly form, a sub n, x to the n. A sub 2, x to the 2, or n minus 1, whatever it is. We'll look at it. Given. Here's the big idea. We'll do this because that's how I always do it. Given f of x equal to this right here, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, all the way down until we get to a1x plus a naught, or a sub 0. And I'm going to let you guys catch up. That is ugly, but I've just saved us a bunch of writing. When we write a function like that, what is this? What is this indicating? Our function is a something. What type of function? It's a polynomial. This thing looks ugly, but all this is think of like a 5th degree polynomial. X to the 5 is the biggest power, right? Is there usually a number connected to it in front, like 4 or 3 or negative 5? Doesn't matter. There's some number connected to x to the 5th, right? In that situation, a sub 5 would be my leading coefficient because it's connected to the x to the 5th. A sub 4 would be the number connected to x to the 4, and so forth and so on. This notation is not nice looking, but it's really, really like dense with meaning. Okay, you give me this thing. Where, or with, a sub n as integers, and I'm going to say a sub n in the set of integers. So it just requires that we have integer coefficients instead of like ugly decimals and stuff. If you give me this, then every single one of the rational zeros, or rational root. You guys want me to use zero or root? Root. Every rational root of f, or of f of x, has the form x equals, I'm going to actually sneak down so it's indented. The root, and you don't have to write this every time, x is going to have the form plus or minus p over q. I should have asked if this was familiar so we didn't have to go super slow if it is. Now there's a natural question that I'm expecting you guys to ask. What's just begging to be asked based on what we've written? Hey, that's the question I'm looking for. That's an important part, right? Where P is equal to a factor of the constant term, which in this big ugly polynomial, which one's just a number with no x's connected? Which a? Everybody agrees it's this one, there's no x. A sub 0, or I much prefer a naught, N-A-U-G-H-T. P is a factor of the constant, and Q is a factor of the leading coefficient. Oh man, there's such cool stuff coming. What's the leading coefficient in our generalized formula for a polynomial? Maybe 1. It could be 1. In this, what's connected to the biggest power of x? A sub n. All right. Now, I'm going to do a lot more talking right now than we're going to write, just so you're aware. We're going to use this to limit how much work we have to do. All of our synthetic substitution and division stuff is going to show back up again right now. And like, we hit it pretty hard, I think, felt like we did, because it's building to this. Our goal by today is we're going to be able to factor stuff, and we're actually just going to jump right in with a problem and annotate the heck out of it. Riley, did you get that last little part of that one? Okay. All that this means, just in case people are still writing that other part, we've seen, and we'll talk about this, we've seen this. It's just a bunch of factors. Check it out. We're going to jump right in with an example. Cool. Oh, it's so fun. Example. I want us to find the zeros, and I'm going to specify all here, and I'm going to write roots because it's shorter, of, and then we'll do a couple of these. Now, language-wise, if I say all roots, that is a bigger term than if I just said find the roots, because normally we find the real roots. This means maybe I shows up. Maybe it doesn't, but maybe it does. So right off the bat, we're going to do a problem that before this, I don't think would have been able to do. Quick question. Does this look familiar? Okay. Cool. Let's do it. On example A, we are going to find all the roots of this lovely function. F of x, we'll say is x cubed minus 7x minus 6. This problem doesn't seem wildly challenging. I'm going to give you about a minute. Talk with your neighbors, try to factor it. And I'm going to come and get real loud next to people as I see you doing something that I'm expecting you to do that's not going to be right. use yours as an example, like I saw two things. Because of all the talking that I did, and it's whether, like, you're not the only person that did this, just so you know. As I looked, this is what I expected people to do. That works if what? It's squared, but it's not squared anymore. So that's out. Everybody else, I love the idea. So this won't work, right? It's not a quadratic. Okay. The other idea, you do not have to write this down, nor do you have to erase it. So we'll go with that gray thing again. I saw a lot of people do this. And this is an awesome idea. I love this idea because if you make a 3 nomial a 4 nomial, maybe you can group it. Until you realize that, right? It just doesn't work. Okay, which means there's an issue that we need to overcome with this then. We don't have the ability until we apply this rational zero theorem or test to actually run this. So let's knock it out. As we go through this, I'm going to talk a lot and annotate a lot. You do not have to write my annotations, just so you're aware. Like, I prefer if your ears are open and you're listening. But let's make a couple observations first. How many roots should we find? And how do you know that? That's which theorem? The degree is 3, and the fundamental theorem of algebra, the corollary to it, but says 3 roots. So I'm already thinking that in my head. You guys agree with that statement? If I can find 3 roots, I should be able to find how many factors then? For every root, you should have 1 factor. So we should be able to find 3 factors. 3 prime linear factors where the number, like that, we'll talk about it. Okay. All right, I know I'm looking for 3. Here's the biggest question. I know that all of my possible roots, and we're going to make this list, and we're immediately applying the rational zero test, okay? You do not have to write this every time, but the first few, it'll help. I know that we're looking for possible rational roots. And I know that they're going to be of the form P over Q. And I'll put that in parentheses. X is going to be plus or minus P over Q. Notice this is exactly what we just said above. We have a polynomial. This is what they'll all look like. What I want us to do is for this problem, just hook it up. P is what? You won't know looking at my board, but if you look at your notes, you can probably see it. Where do we get P and Q from? P is the constant term. What is the constant, or a sub 0, in this function? So don't care about the negative, but you're absolutely right. It is negative 6. All I care about is the 6. It's plus or minus. Let's start thinking about the factors of 6. Give me the first number that goes into 6. 1. Good. I agree with you. 1 goes into 6. I think we can probably all agree. Give me another number that goes into 6. Another one. And? 6. Okay. There are 4 possible numbers, P. What is a leading coefficient? Try again. Louder? 1. Because it's how many x cubed? A is 1, or Q, I'm sorry, is 1 in this problem. Tell me the factors of 1. Okay, easy. Now, this example doesn't really change it much, but we've just found 8 possible roots. Now, here's the really awesome part about this. Our goal is factoring, and there's a million different applications where finding the roots of something means something meaningful in whatever context. I have 8 possibilities right now. Is guessing and checking a valid way to do math? Totally valid. 100% yes. Is it really our best option, though? I claim there's 8 numbers. Can you find me the 8 possible roots we just found? So, what are they? How many? 8, we know. Give me one of the numbers. 1 over 1 is 1. Give me another one. Negative 1 and 2 and negative 2 and 3 and negative 3 and 6 and negative 6. Those are all 8 of them. Now, this problem you could guess and check. And we'll see this afterward, but I'm going to make us actually use the whole test to do this. All right. How do you know if something's a root? What should it spit out if we plug it into the function? It should spit out a 0. Now, if I find something that is a factor and we divide it, maybe synthetically, would we get another factor as the quotient? So, to make sense of that, if I say that 3 is a factor of 27, and you don't have to write this part, this is just me talking, I should have changed. We're going to get 9 here and a remainder of 0, right? So we've determined that 3 was indeed a factor. What's the other factor we just discovered? 9. Okay, that idea we've used with synthetic division. We're going to use it again right now. So let's check these. This part can be tedious. I will show you on your calculators how we can avoid this. I'm going to start trying in a systematic method. Anybody have a suggestion for the number we should try first? I know it should spit out a 0. Let's try 1, maybe? Let's just see if it works. I'm going to use synthetic substitution. And I'm doing this because instead of just saying what's f of 1, I don't know why I did that. Instead of just saying what is f of 1, I'm really checking if x minus 1 is a factor, what's another factor I get? Because I need that. So here we go. I'm going to do synthetic division or substitution, depending on how you want to think of it. Synthetically divided by x minus 1, or evaluating f of 1 using synthetic substitution. Is that too many math words in a row? Synthetic division and substitution are the same thing. When I refer to synthetic substitution, it's when I said, hey, find f of 5 using synthetic division. The remainder is the substitution part that I'm thinking of. Okay, what populates for this function f of x the top row? 1, 0, -7, -6. Okay, let's try. 1 times 1 is 1, plus 0 is 1, times 1 is 1, is -6, is -6, is -12. I don't need to talk that out loud. I'm so sorry. I shouldn't do that because you're likely doing the math as well. My bad. Did we learn anything just now? It's not a factor. So, this part, you don't have to write every time. This whole work implies x minus 1 is not a factor. Everybody cool with that? Okay, what might you try next? There's not a right choice, just so you know. You would try -1 next? I want you guys to try synthetically dividing by x plus 1, or changing the language, synthetically substituting -1. Try -1. I'm sorry? Because remember that if I want to divide by x minus k, like if I'm dividing something by this, I put k on the outside. What do we just put on the outside? So it would, if we plug 1 in here and a 1 in here, that's our factor. Because this is the real, so we're doing it synthetically. What we really just did, if I'm checking, and I'm going to connect all these pieces. If x equals 1 is root, then can you tell me a factor? And I'm going to switch this around real quick. This is a different question. If x minus 1 is factor, what's a root? Yeah. Do you agree with that statement? So that went this direction, but it also goes this direction. Okay. Did -1 work? Ooh, I saw yes and no. I don't know for sure. I'm going to check. All right, let's try -1. Now, don't erase stuff. Like, I'll show you guys a shortcut so we can save a little time here so that you'll only ever have to really do 1. But let's check to see if this one worked. 1, 1, -1, 1, -6, 6. Ooh, it did work. Now, just so you know, I already knew it was going to work because -1 cubed is -1 plus 7 minus 6. Like, I could do it here. You will not always be able to. Beyond that, just knowing -1 works doesn't get me the other part. So check it out. This is going to have to get dragged and moved up. This is the most important thing that we're going to see in this whole problem right now. As soon as we do this, what does this imply we know about x minus -1 or x plus 1? Is a factor. Now, I'm writing way more than I'm going to expect you to on a regular problem. Huggins, we tried 1. It wasn't a 0. It wasn't a factor. We tried -1. It spit out a 0, so it is a factor. Okay. I need to zoom out so I can move this because I want to be able to see all of it at once. So I'm going to take this whole problem. Are we going to cut it? I'm going to move it up here. Maybe. Boom. All right. This is super duper important. The fact that x plus 1 is a factor is not all that we know. Because I wish I had a good infomercial voice. We now know. I'm going to say we now have. We now have a new version of f of x. Before, it was just that x cubed thing. I don't even remember what it is. What's one of the factors that we know for sure? X plus 1 was one factor. We just verified that. What's the other factor we just discovered? X squared. 1x squared minus 1x, which I'm just going to write minus x, minus 6. We have a more factored form, and all of a sudden, our old rules start to kick in. X plus 1 is a prime linear factor. It cannot go any further. How about the other thing? Can this factor more? And I think so. So check it out. I'm going to change color. Now, factor. I'm just going to say now factor, but I'm going to say more. Now factor this using the old methods that we know. And I'm going to give you a minute. I want you to factor out that quadratic. Realistically, it should take 20 seconds max to factor that. Why you write I can't tell. We just copy. Right? Okay. How do you get these? Whoa. Are these 3s? So check it out. We're going to take this and this and we're going to multiply, right? We have a shortcut waiting because it's a 1. Give me factors of -6 that add up to what do those add up to though? So they multiply to be that, but they add up to 7, right? So they have to multiply to be 6. I don't think 1 and 6 is going to work. Give me 2 more numbers to get to 6. Okay, which one should be negative if you want to add up to negative? What's 3 plus -2? Good. So I know that my numbers are -3 and +2. My factors are x minus 3, x plus 2. All right. Looking at this, I used a shortcut. Did you guys use a shortcut? Okay. When we go to our next line, I will look at this. Remember factors of -6 that add up to -1. What were they? -3 and +2, or +2 and -3, however you want to word it, right? Okay. Are we just going to leave behind our original x plus 1 factor? No, they come along for the ride. X plus 1. And you've said leading coefficient 1, shortcut, -3 and 2, right? X minus 3 and x plus 2. We now have a complete factorization. What degree was our original function? 3. Are all of these x to the first power, as in linear? Did we just write our x cubed as a product of 3 linear factors? We just used the linear factorization theorem. I'm cool with it. Okay. What was the actual question asking us to do, though? Okay. How many are we expecting? So there are 8 possible. If we go back and check at our list, let's find these roots first. What are the actual roots of this thing? X equals, and to find these, we just said each factor equal to what? If you said x plus 1 equal to 0, what do you get for x? Try again. -1. If you said x minus 3 equal to 0, +3. And if you set x plus 2 equal to 0, all right. I want you guys to make sure you write those down because I'm going to scroll back up to look at something. Okay, we found 3 linear factors. Linear factorization theorem. We found 3 roots. Fundamental theorem. We used the rational 0 test for a second, but check it out. -1, 3, and -2. Is -1 show up on here? -1 over 1. Are you sure? What's negative? So plus or minus is -1, or negative version of it, 1 over 1. Is that the 1 I was looking for? Does 2 show up in this if you pick positive or negative and you just use these fractions? 2 is just 2 over 1, right? Is the other one -3? Does the number 3 show up when you write these fractions? Every single root that we just found was in that list of 8. Every single one of them. It will always happen if we have real rational roots. Okay. We did an easier one here. Did it agree with all the theorems that we talked about today? Now that we finished it, do you remember seeing this ever? You saw it last year. This theorem? The rational zeros? I wish I had an Algebra 2 book so bad. I wish I had one. Do I have one? You guys didn't go out of the book last year, did you? You did use the Algebra 2 book last year? Okay. I'm going to go get an Algebra 2 book so that I don't have to keep asking you guys if you've seen this. Cool. Let's do another one. Huggins, did you get your question addressed? Yeah. Okay. Was it a good one?
Was it a good question?
Yeah.
Probably not.
Oh, I don't know about that. All right. Let's do a more fun one. Okay. F of x. All right. We ready to get cooking? We have a new function, f of x. We're still finding all zeros. 3x cubed minus 20x squared plus 23x minus, just kidding, plus 10. All right, before we jump in, we get this ugly thing. How many roots are we going to find? 3. Why? So that's okay. What's the degree of this function? 3. A cube. Yeah, you're right. It's a third degree function. 3 roots. Which means we should find how many linear factors? 3 of them. Okay. Now, with that in mind, when we see something like this, how many terms does it have? There's 4 terms. There's an x cubed, an x squared, an x, and a constant. Before I take the time to try this whole fancy process that we're talking about, in my head, I'm going to try to group it first. If it's 4 terms or 6 terms or 8 terms, I'm always going to try to group it first. I can't find anything nice that goes into 3x cubed and 20x squared. I mean, I can, but it's only x squared. I can't find anything between 23x and 10. I can't group these. But that's okay. We're going to start our list, or start our problem by, let's figure out like what the possible ones will be. So I'm going to use some shorthand. If I write pos with that Q, that's shorthand for what? Possible, rational, roots. Okay, so I know it's going to be the form, possible rational roots are going to be of the form x equals plus or minus, and I'm going to start taking factors. P is what? The constant, and specifically, what is it? 10. What are factors of 10? And I'm always going to start my list low. Does 1 go into 10? Does 2? Does 3? No. Does 4? Does 5? And so does 10. Okay. 4 possible numerators. What's Q in this problem? 3. What are the factors of 3? 1 and 3. Bigger question. Don't worry about repeats right now. How many numbers did we just write there? So let me rephrase that. How many rational numbers did we really just write? Like that answer. Go ahead.
What's Q?
Factors of this.
Factors of the leading code.
Yep. I heard 16. I agree. Okay, this part, I don't love the idea of doing this, but we're going to do it one time. If we wanted to write all these out, and I hate this, please don't make this the norm. I get 16 numbers. I'm only going to write 8 of them because plus or minus is the double. Check it out. What are the possibilities for my denominator? Could be a 1 or a... Okay, and I have numerator. If it's a 1 that we choose, I would get plus or minus 1 over 1, 2 over 1, 5 over 1, or 10 over 1. I'm just using the 1 as a denominator. I've tried every possibility. What else could be my denominator, though? 3. So it could be instead 1 over 3, 1 over this 3, or 2 over 3, or 5 over 3, or 10 over 3. Why is this 16 when I've only written plus or minus? Okay. I want you guys, I'm going to nudge you in the right direction. I want you to start this problem. I'd like you to finish it, but I understand that maybe you can't. Instead of doing plus 1 and minus 1 and plus 2 and minus 2, here's my suggestion. And what I do, not really a good suggestion, but for this one it'll help. Start at 1, and then try 2. And if it doesn't work, try 5. If it doesn't work, try 10. And then once you go through all the positives, then try the negatives. Try 1 and 2, see if either of those is a root, in turn producing a factor. Tonight, finish this. If nothing, yeah, finish it. That's it. I'm going to check it tomorrow. 1 out of 1 if it's done, right or wrong. Cool. Later, Raiders.